Hello everyone, we are actually dealing with the module 1 of network analysis course, and so far we have discussed about the Kirchhoff's laws, the source transformation techniques. In the last class we have discussed about the mesh analysis. Moving further, today we will discuss about the AC circuits. Okay, and these circuits, you may be observing there, these circuits consist of L and C components along with R, that is the resistance. Okay, so here we consider the excitation of the circuits by sinusoidal sources. Okay, and whatever the AC sources we are considering, they are only the sinusoidal sources. And so far we have discussed the DC circuits in which we were not finding the L and C components. For the simple reason, in the DC circuits the excitation will be DC, and for the DC in the steady state the inductor acts as a short and capacitor acts as open. Okay, so for that reason, so we are not considering the L and C components, okay, in the case of DC circuits to obtain the steady state responses. Now in the case of AC circuits, these offer some finite value of reactances, and to keep it simple, they will not act as either short or open. Now so you cannot have an equivalent of it. Okay, so L will be still L and C will be still C. Okay, so the AC circuits will consist of L and C components along with R, and the excitation will be the AC, and in our case we consider the AC sources to be the sinusoidal sources. Now consider an AC circuit shown below. Now this is the AC circuit, so this is the voltage applied and this is the current that goes into the circuit. Let us consider that this to be the excitation, okay, and this to be the circuit current to be the response. Now let the applied voltage, okay, V of t is equal to Vm sin omega t plus theta 1, and you know very well that the sinusoidal waveform is characterized by three parameters: Vm, the amplitude Vm, then the frequency omega, then the phase, that is theta 1. Okay, in this case it is theta 1. And what we have to remember is, okay, if the excitation is sinusoidal with the frequency of omega, the response will also be sinusoidal and the frequency of the response will also be omega. And what is that which changes? The amplitude and the phase. But please remember, this is true for the linear circuits. That means those circuits which whose response will be linear to the excitation. And RLC circuits which we are dealing, okay, they are all linear circuits. So if the excitation is sinusoidal, then even the responses will be what? Sinusoidal of same frequency. Then what is that which is going to change? The amplitude and the phase. So that is why let the applied voltage V of t equal to Vm sin omega t plus theta 1. The circuit current that flows is I of t and is given as I of t equal to Im sin omega t plus theta 2. So the amplitude and the phase would be different in the case of response, whereas the frequency will remain same as omega. Now these two sinusoidal quantities can be represented by phasors. Okay, this is in the cause of analysis. Okay, what we do is we consider these sinusoidal quantities to be the phasor quantities. Okay, so to help the cause of analysis. Okay, these two sinusoidal quantities can be represented by phasors. Then what is a phasor actually? A phasor is a rotating vector in the complex plane. Okay, just like the one which is shown here. The sinusoidal signal, whatever we are seeing here, is now viewed as a rotating vector in the complex plane, and the vector will have the magnitude, and the magnitude of this vector is same as the amplitude given here, and rotates with what? Rotates with time. Okay, rotates with time in the anti-clockwise direction, because as time progresses, the angle goes on increasing, and when the angle is increasing, it is actually what? The movement in the anti-clockwise direction. and rotates with the time at an angular frequency of omega, right. So, that is what is written here. These two sinusoidal quantities can be represented by phasors. A phasor is a rotating vector in the complex plane. This is shown in the figure, which is a voltage phasor. Okay. Now, this is regarded as the voltage phasor. The phasor has a magnitude of Vm and rotates at an angular frequency of omega with the time. Then what you are observing is the theta 1. What is this? This is the angle traced by the phasor, okay, at our point of reference t is equal to 0, Now, the voltage phasor, okay, which is now representing the given v of t, is now given by Vm at an angle of theta 1. Okay. So, Vm at an angle of theta 1. We are considering the angle, whatever the angle, okay, to be at t is equal to 0. When we do so, we are eliminating what the frequency information, but that is not a problem because even the response will have the same frequency. So, the voltage phasor, whatever we are considering for v of t, that is the applied voltage, is actually Vm at an angle of theta 1, which is at our point of reference t is equal to 0. Also referred as the polar form of phasor. Now, this particular representation is also referred as the phasor form, okay, or the polar form of the phasor. Okay. So, the rectangular form is just the Vm cos theta 1 plus j Vm sin theta 1, and all these, the polar form and the rectangular form you may be aware of, okay, while you were dealing with the complex numbers. Okay. Right. So, the phasors are after all what the complex quantities, The voltage phasor is given by Vm at an angle of theta 1. This kind of representation is also called as the polar form representation of phasor. The rectangular form is Vm cos theta 1 plus j Vm sin theta 1. Similarly, now the current phasor is given by what? Im at an angle of theta 2, also referred as polar form of phasor, phasor current rather. Next, the rectangular form is Im cos theta 2 plus j Im sin theta 2. Okay. Now, the ratio of voltage phasor to the current phasor is called as the impedance, Now, in our case, we are considering the voltage phasor, that is actually the phasor applied to the circuit, and the current phasor, okay, whatever that is, impressed into the circuit. So, basically the ratio of voltage phasor to the current phasor refers to the impedance Z, and this impedance now can be regarded as the impedance of the circuit, because whatever the voltage phasor we are considering, it is the voltage applied to the circuit, and whatever the current phasor we are considering, it is the current, that is, it is representing the current that flows into the circuit. So, this impedance whatever we are considering, which is the ratio of voltage phasor to the current phasor, is that of the circuit. So, what we are seeing here is Vm at an angle of theta 1 divided by Im at an angle of theta 2. So, Vm by Im, okay, the complex number representations, okay, in the polar form, when you take the division, so the magnitudes divide, whereas the angle difference we find. Okay. So, Vm by Im at an angle of numerator angle minus the denominator angle. So, Vm by Im at an angle of theta. So, this is the representation of the impedance, okay, in polar form. Now, you can also write this in the rectangular form as Vm by Im cos theta plus j Vm by Im sin theta, where theta is theta 1 minus theta 2. And one more thing what we have to remember here is the impedance, although a complex quantity, okay, it is not a phasor, Now, as already told, what is a phasor? It is a rotating vector, it rotates with respect to time. So, that means it changes its angle with respect to time. So, this actually means, supposing the impedance, if it is not a phasor, it means that with respect to time, this particular angle doesn't change, whereas the voltage and current phasors, they do change their angle with respect to time. Okay. And whatever we are representing here, the phasors of voltage as well as the current, they are at our time, reference time t is equal to 0. Please remember that. Okay. Actually, they do vary with the time, the angle do vary with the time, whereas the angle associated with the impedance does not vary with time. So, it is a complex quantity, no doubt, but it is not a phasor. The simple example I would like to give you, let us say that this Vm at an angle of theta 1 is what is the this theta 1 is the angle traced at our point of reference t is equal to 0. Then theta 2 is the angle traced by the current waveform at t is equal to 0. With the time increase, okay, the angle keeps on changing. Say this theta 1 changes by what? Changes to theta 1 plus 15, say, in a given time. Then the current also will change its angle in the same time by the same degree. That is, even the angle here would be from what? From theta 2 to theta 2 plus 15. Again the difference will be what? Theta 1 minus theta 2. This is because both the current and the voltage, they both have same angular frequency. So in a given time they would have traced what? Same angles. So that is why we say the impedance is not a phasor. Okay, this particular angle will remain as it is for any given time, whereas these two angles do change with respect to time, but we are considering at our point of reference t is equal to 0. So the impedance, although a complex quantity, but it is not a phasor, as with respect to time the angle of impedance do not change. Let us keep this in mind. Now if the AC circuit above is represented equivalently by a single resistance, okay, let us consider the AC circuit to be a network of resistance and you can effectively replace them by a single resistance, say R. Then impedance of the circuit Z is actually equal to Vm at an angle of theta 1 divided by Im at an angle of theta 1. Earlier there was theta 2 here, now theta 1, for the simple reason the resistance do not provide any phase difference between the voltage and the current. This we have seen in our basic courses. Okay, since in resistance there is no phase difference between voltage and current, and so theta 2 is equal to theta 1. So Z is equal to Vm by Im at an angle of 0 degree. So Vm by Im, you know, in the rectangular form, Vm by Im cos 0 plus jVm by Im sin 0. So ultimately turns out to be Vm by Im, which is actually equal to R. So in the case of the resistive network, the impedance of the network is actually equal to the equivalent resistance between the terminals of the network, which is equal to R. Okay. Now if the AC circuit above is represented equivalently by the single inductance, okay, then that entire AC network which we have shown here, okay, this AC network, whatever we have shown there, if it is equivalently between these two terminals, if we can equivalently represent this by a single inductance, then what is the impedance of the circuit? Okay, if the AC circuit above is represented equivalently by a single inductance, then Z is equal to Vm at an angle of theta 1 divided by Im at an angle of theta 1 minus 90, for the simple reason that in the case of an inductor, current lags the voltage in phase by 90 degree. So since in inductance current lags the voltage in phase by 90 degree. So the impedance of the circuit, or in general any inductance, is actually equal to Vm by Im at an angle of 90, Vm by Im cos 90 plus j Vm by Im sin 90. So j cos 90, you know, it is 0, then j Vm by Im sin 90 is 1, so j Vm by Im. So Vm by Im, what you should know in the case of an inductance is the peak value of the voltage to the peak value of the current is always equal to the reactance of the inductance, which is omega L. Okay, so the impedance of the inductance now can be regarded as j omega L. Okay, that's what has been given here. In inductance, the ratio of peak value of voltage to peak value of current is always the reactance, which is given by the omega L. Now we can say any inductance of L Henry can be equivalently represented by impedance of j omega L ohms. Okay, L in Henry now in the AC analysis can be equivalently considered to be what? Impedance of j omega L ohms. Okay, right. Now if the AC circuit above is equivalently represented by single capacitance, then Z is equal to Vm at an angle of theta 1 divided by Im at an angle of theta 1 plus 90. This is because in the case of a capacitor, current leads the voltage in phase by 90 degree. Okay, so Z is equal to Vm by Im at an angle of, you know, theta 1 minus of theta 1 plus 90 will be giving what? Theta 1 cancels, then minus 90 will remain. So Vm by Im cos 90 minus j Vm by Im sin 90. This is the rectangular form. So, this is anyway 0 minus j Vm by Im sin 90 is 1 minus j Vm by Im minus j Vm by Im, you know, it is the reactance of the capacitor, which is given as 1 by omega c. So, the impedance of a capacitor is actually minus j by omega c. In that is what has been written. In capacitance, the ratio of peak value of voltage to peak value of current is always the reactance, which is given by 1 by omega c. Now, we can say any capacitance of C farad can be equivalently represented by impedance of minus j by omega c ohms in the AC analysis. Okay. Now, we will take up a problem related to this. Strictly speaking, this discussion related to the representation of the sinusoidal sources and responses in terms of phasors is an elaborated discussion. Whatever that is required for the smooth conduction of this course, I have considered. Now, let us take up a problem related to this. So, find the current through the capacitor in the circuit shown in figure 16. Okay, that is this figure itself. You have to use the mesh analysis. Now, this is an AC circuit. You are observing that this is an AC circuit. Okay, now this is the inductance, which has got the impedance of J4 ohms, then 2 ohms resistance, 3 ohms resistance. Then you are observing what? An impedance. Okay, which is basically what? An impedance of the capacitor, which is actually equal to minus J2 ohms. Now, this is the AC source, okay, and this is one more AC source, 10 cos 2t plus 45 degree. Okay, so the angular frequency in both the cases, it is 2 radians per second. Okay, 2 radians per second. Now, we will consider these to be the phasors, and then consider the mesh analysis, and it will equally work well for the phasor representations. And when we calculate the response, even it will be in phasor form, and when once it is obtained in phasor form, you can convert that to the sinusoidal form, because as already told, if the source is sinusoidal, in the case of linear circuits, the response is also sinusoidal of same frequency. Only the amplitude and the phase, they are going to change. Now, let us take up this problem. So, now 5 cos 2t. Now, omega is 2 radians per second. What is the phase? Phase is 0. So, this can be easily regarded as 5 at an angle of 0 degree. Then, what is this? 10 cos 2t plus 45 degrees. This can be easily regarded in the phasor form as 10 at an angle of 45 degree. So, that is what has been shown here, 5 at an angle of 0 degree, 10 at an angle of 45 degree. Okay? Right. Now, what we have seen earlier, okay, while discussing in the beginning of the discussion of the AC circuits, basically the sine waveforms were represented in phasor forms. Please take it from me, even the cosine waveforms, okay, like this can be represented in phasor forms in the same way as what we have done for the sinusoidal, sine function waveforms. Okay, right. So, 5 at an angle of 0 degree, 10 at an angle of 45 degree. Okay, then J4, 3 ohms, 2 ohms minus J2 ohms. Now, we will see what was our question. Our question was find the current through the capacitor. Okay, so let us see what is the current through the capacitor. Now, you have to use a mesh analysis. There are 3 meshes, 1, 2, 3. Okay, and I1 is the current associated with mesh 1, I2 is the current associated with mesh 2, I3 is the current associated with mesh 3. Okay, so current through the capacitor is I3. It is easily observable because this particular arm or the branch belongs to only mesh 3, and the current in this branch should only be I3. So, the current that flows through this capacitor should be I3. So, our objective is to find I3 using the mesh analysis. Okay, and we are considering the AC circuits here. Okay, now the circuit has been written there. The circuit has been written here. Okay, so now we will apply the mesh analysis. Yesterday I have told you that we will first identify the meshes, then the corresponding mesh currents, then we will apply KVL to each of the meshes, and we will get what? If there are 3 meshes, we will have 3 equations represented in terms of what? The I1, I2, I3, the mesh currents. Then when we solve those equations, we will get the values of the mesh currents, right? Okay, so apply KVL to mesh 1. mesh 1. So, let us start from here. So, this J4 is shared between what 1 and 3. So, plus J4 into I1 minus I3. Yesterday I have told you, in the case of the potential drop across the passive circuit element, you first write plus, then the passive circuit element impedance or resistance value multiplied by the current. In the case of shared component, if you are applying KVL to mesh 1, okay, you will write it as what I1 minus I3. Supposing if the same voltage drop across J4, okay, was written while applying KVL to mesh 3, so you would have written what plus J4 into I3 minus I1, okay, and everything will be automatically taken care. This we have seen in the last class. So, J4 into I1 minus I3 plus 2 into I1 minus I2, then minus 5 at an angle of 0 degree is equal to 0. So, there are 3 components, we are done with this. Next, we will properly arrange this equation. So, I1 terms, so J4 I1, 2 I1, so 2 plus J4 I1, then I2 minus 2 I2, then minus J4 I3, then this comes to the right hand side, 5 at an angle of 0 degree. 5 at an angle of 0 degree can be regarded as what 5 cos 0 plus J5 sin 0, sin 0 is 0, so 5 cos 0, 5 cos 0 is what 5. So, call this as equation 1, call this as equation 1. Now, apply KVL to mesh 2, apply KVL to mesh 2. So, let us start from here, plus 3 into I2 minus I3, then plus 10 at an angle of 45 degrees, then plus 2 into I2 minus I1 is equal to 0, is equal to 0. Now, arranging the terms properly, this implies, so minus 2 I1, then 3 I2, 2 I2, 5 I2, okay. Next, minus 3 I3. Then this goes to the right hand side, minus of 10 at an angle of 45 degree. Now, let us convert this into what? The rectangular form using the calculator, and this will be 7.07 plus J 7.07. When I multiply minus, so you will have minus 7.07 minus J 7.07. Call this as equation 2. Call this as equation 2. Next, apply KVL to mesh 3. Apply KVL to mesh 3. So, let us start from here, minus J2 I3, for the simple reason that this is not shared with any of the meshes again, right. So, minus J2, all I have told, we are not writing this plus. Had we written plus, again plus into minus would have been minus, that is all. So, plus into the passive circuit element impedance or resistance and multiplied by the corresponding mesh current, that is what we have done there. Then plus 3 into, then I3 minus I2, then plus J4 into I3 minus I1 is equal to 0. So, now we will arrange these terms properly, minus J4 I1, then minus I2 terms I have to find 3 minus 3 I2, then I3 terms. So, it is J4 minus J2 plus 3, then plus J4, J4 minus J2, J2. So, 3 plus J2, 3 plus J2, I3 is equal to 0. Call this as equation 3. Call this as equation 3. Now, this particular set of equation can be represented in matrix form. So, 2 plus J4, then minus 2, and then you have minus J4, and then you have minus 2, and then you have 5, then minus 3, and minus J4, minus 3, then 3 plus J2. So, then I1, I2, I3, so which is now equal to 5, and then minus 7.07 minus J 7.07, and then 0. So this is the matrix equation. Now our objective is to find what? I3. Okay. So I3 is nothing but capacitor current. Okay. So using Cramer's rule, so we consider the delta. So 2 plus J4 minus 2 minus J4 minus 2, 5 minus 3, then minus J4 minus 3, 3 plus J2. This determinant we have to now evaluate. This is equal to this. There are two terms, let us put this in brackets. Then the square bracket opens, which is actually evaluating the inner determinant, like 5 into 3 plus J2 minus 9. Okay, this is the first main term of the determinant. Next, minus into minus plus 2 minus 2 into 3 plus J2, then minus 3 into minus J4. So minus J12. Okay. This minus 3 into minus J4 is plus J12. There is an inherent minus. Okay. So minus J12. Then minus J4. Again square bracket opens. Okay. Minus J4. So minus 2 into minus 3. 6. Then plus. There is an inherent minus which gets multiplied with this minus. So plus J20. So this is the determinant. Now you have to use the calculator in the complex mode and then type as it is. Okay, when you expand the determinant and properly. So what you can do, use the calculator in the complex mode and type as it is. The only change in the calculator is, instead of J4, you have to type 4i in the ENG button, corresponds to the imaginary number. You have to press that to get I. Okay, so 3 plus 2i you have to type. Rest the same order has to be maintained. As soon as you press is equal to, you will get the correct answer. Right. So we will see. Plus 2 into minus 2, 3 plus J2. I am just cross checking. So minus J4 into 6 plus J20. So this turns out to be, so therefore delta is now equal to 40 minus J12. So we got delta now. So now we need to calculate delta I3. So delta I3 is now equal to, okay, so you know what to do. If I have to find I3, now this one, the right hand side should be substituted in the third column. Okay, all these are basics, I think you should be knowing. So 2 plus J4 minus 2 minus J4, then minus 2, then 5 minus 3, then 5 minus 7.07 minus J7.07, and then 0. Now we will expand this determinant. So 2 plus J4, square bracket opens, 5 into 0, 0. Then there is minus plus. So 3, then minus 7.07 minus J7.07. Okay, so this is the end of the first term. Then plus 2, square bracket opens. This is 0, minus 2 into 0, 0. Then there is inherent minus that gets multiplied with this minus. So plus J4, and then into this minus 7.07 minus J7.07. Now the square bracket closes. Then next plus 5, square bracket opens, 6 plus J20. Okay, so let me cross check. Delta I3, 2 plus J4 plus 3 into minus 7.07 minus J7.07 plus 2 then J4 into minus 7.07 minus J 7.07 plus 5 into 6 plus J 20. Yes. Then we will now use the calculator in the complex mode to get delta I3 as 128.98 minus J 83.82. So therefore, I3 is now equal to delta I3 divided by delta. In the calculator, you have to substitute this in the brackets. 128.98 minus J 83.82 whole divided by 40 minus J 12 in the brackets, because this represents a single complex number. Then I3 you get it as 3.535, okay, then minus J 1.035. This can be regarded as, this is in the rectangular form. So whatever we have obtained is what? When the sources are in the phasor form, even the responses will be in the phasor form. So when I convert this into polar form, what do I get? So 3.68 at an angle of minus 16.31 degrees amperes. So this is the phasor of the current response. Now if I want I3 of t, so I3 of t is now written as, I3 of t is now written as, this represents the amplitude. So 3.68. Now the function whatever was there from which we got this phasor forms, was the cosine function. So you have to blindly write the cosine, then omega doesn't change, so 2t, then minus 16.31 degree amperes. So this is I3 of t. So basically what we do, we represent the phasors at our point of reference t is equal to 0 and obtain the response phasor which is again at t is equal to 0, and then this response at t is equal to 0 gives the information about the amplitude as well as the phase angle. Then this one can be used to obtain the steady state expression like this, in the cosine function form in this case. So had the sources been represented in sinusoidal form using the sine function, then you would have got the response in terms of phasors, but when you write the steady state expression like this, you would have written sine, that's all. So this is called as the steady state expression, because the current will follow this particular expression in the steady state, and steady state is the state when the circuit has completely settled down. And more on this will be touched in the initial conditions chapter. So this actually marks the end of the problem, because our objective was to find the capacitor current, and which we have effectively found. So that is the end of the problem. Now we will see the node analysis. So what we have done in the case of mesh analysis, in the last class we have basically seen the illustration of the mesh analysis, how mesh analysis is carried out. Then we took up problems related to the DC circuits. Today we have taken up a problem in the case of mesh analysis related to the AC circuit. Now we will go to another method of analysis of network, which is actually a node analysis. Now even this node analysis is illustrated by considering a problem. Let us see. Node analysis illustration. First of all, what is a node? A node is basically a point where two or more circuit elements join. Right. So now let us consider the problem. So this is the 10 amperes, then then this is, you know, whatever I am now considering is the conductance, not the resistance. So, which can be, you know, 2 mho, and this can be 4 mho, and this can be 3 mho, and this can be, you know, 2 amperes. Okay. Now, in the node analysis, what we do? First, we identify the nodes. That means those points where 2 or more circuit elements join. Okay, like, you know, in this case there are 3 nodes. This is the first node wherein this circuit element, and this circuit element join. This is the second node where this circuit element, this circuit element, this circuit element join, and this is the third node wherein, you know, this arm, this arm, this arm, this arm all are connected. So, there are 3 nodes. So, we have identified the nodes. Then what we do? We will identify the ground node, okay, where, you know, the potential is considered to be 0. So, usually the bottom node is considered to be the ground node. So, now this is the ground node where the potential is considered to be 0. So, ground node. Now, leaving this ground node, there are 2 more nodes, 1 as well as 2. So, we will consider this as node 1 and this as node 2. And after identifying the other nodes, what we do? We consider a voltage, okay, at each of the nodes. Say the voltage here is V1, the voltage here is V2. Now, what is this after all voltage, okay, at a node 1? Voltage at a node 1 refers to the potential difference between the node 1 and the ground with ground as reference. So, V1, if I am saying that it is the voltage appearing at this point, it actually means it is the potential difference between this point and the ground point with ground as reference. Okay. Then similarly V2, V2 is the potential difference between the node 2 and the ground with ground as reference. So, plus minus V2. Okay. Right. So, what we have done in the node analysis, we have identified the nodes, we have identified the ground node, we have identified the other nodes and considered a voltage at each of the nodes, remaining nodes, whatever we are observing. Now, what is to be done? We need to apply KCL at each of these nodes, okay, barring the ground node. So, we will not apply KCL to the ground node, even you can apply there, but of no use. Without that also you can still obtain the response of the network. Okay. So, what we will do? We will apply KCL to each of the nodes available except the ground node. So, let us start from here, node 1. So, apply KCL at node 1. Now, let us strictly follow the statement of the KCL, whatever we have discussed in the very first class. What is that? The algebraic sum of branch currents that leave a node is equal to 0. So, we will only consider what? The leaving currents, okay, at a node. And ultimately, you know, you have seen while I was discussing the Kirchhoff's current law, when we considered that statement, ultimately when the equation was rearranged, it was nothing but what? The equation of the sum of incoming currents is equal to the sum of outgoing currents, which you have seen in your basic courses. Okay. But we will strictly follow the statement whatever we have stated. What is that? The algebraic sum of branch currents that leave a node is equal to 0 at all instants of time. So, we will apply now KCL at node 1. Now, what we have to remember here is, you know, this is V and this is R. Okay. What does this V actually represent? It is the potential difference between these 2 points. Okay. Or you can say with this as reference, the potential here is V. Okay. Or as compared to this point is higher in potential by V volts. So, this I, whatever is there, is now equal to what? V by R. Now, you know, if I consider this as ground, the same arrangement can be written something like this: V, then R, then this is the ground. Okay, the same if I consider this as ground, and then the I should be same as what? V by R, and that can be found as, you know, the current always is flowing from higher potential point to lower potential point. So, V minus 0 by R. So, which turns out to be what? Same V by R. Now, in the case of, you know, 2 nodes, you know, having the potentials of V1 and V2, okay, with respect to ground. So, what you need to do, if I have to find the current I through R, what is this V1? V1 is the potential difference between this point and this point with this as reference. The other potential whatever you are identifying, it should also be with respect to the same reference, that we have to keep in mind. So, I in this case again is given as V1 minus V2 by R. Now, this is in the case of resistance. In the case of conductance, V1, V2, say these two voltages are considered to be with respect to the same reference. Then if I have to find I through G, it is the conductance reciprocal of the resistance. So, I in this case is actually V1 minus V2 into G. So, thus 1 by R is written as G. So, this is in the case of what? The conductance. So, let us remember all these facts, right. So, apply KCL at node 1. So, we are considering the leaving currents, right. So, what is the current that comes out of this node in this direction? So, minus 10, because 10 amperes if it flows in this direction, it also means that minus 10 ampere is flowing in this direction. Yes. Next, we need to consider the leaving current here moving in this direction. So, the voltage here is V1 with respect to ground. The voltage here is 0 because this is the ground node. So, the potential difference is what? V1 minus 0. So, V1 minus 0 divided by 2 in the case of this being ohm, but into 2 because of the presence of mho. So, what I will do, V1 minus 0 anyway V1, so then into 2, okay, right. Next, this is also the branch associated with node 1. Again I have to consider the leaving current. So, V1 minus V2 into 4. So, V1 minus V2 into 4, and then there are 3 branches associated with this node. So, there are 3 terms. So, then this should be equal to what? 0. This should be equal to 0. So, when I properly arrange this, what is that you are going to get? 2V1 plus 4V1, 6V1, okay. Then minus 4V2, then minus 10 comes to the right hand side, becomes plus 10. Call this as equation 1. Now, apply KCL at node 2. So, what is the current that comes out of this node in this direction? It is plus 2. What is the current that, because this is in fact what? This current was entering, this current is leaving. So, you assign what? Positive sign. What is the current that comes out of this node in this direction? It is, the potential here is V2, the potential here is 0. So, V2 minus 0 into 3. So, 3 into V2. What is the current that comes out of this node in this direction? So, it is V2 minus V1 into 4, leaving current, okay, that of corresponding to this particular node is V2 minus potential difference into the conductance. So, this should be equal to 0. Now, when I properly arrange this equation, minus 4V1 plus 4V2 plus 3V2, 7V2 is equal to minus 2, call this as equation 2. Now, these two equations can be arranged in the matrix form: 6 minus 4 minus 4, 7 multiplied 2 V1 V2, so which is equal to 10 minus 2. Now, using Cramer's rule, what is delta? Delta is 6 minus 4 minus 4, 7, so which is 42 minus 16, 26. Then delta V1, which is equal to, right hand side should be substituted in the first column. So, 10 minus 2 minus 4 minus 7, okay, minus 4, 7. Then this is equal to 70 minus 8, 62. Then delta V2 is equal to, right hand side should be substituted in the second column, 6 minus 4, then 10 minus 2, so minus 12 plus 40, so which is equal to 28. So, how V1 and V2 can be calculated? So, V1 is delta V1 by delta, so which is what? The 62 divided by 26, so V1 will be 2.384 volts roughly. Then what about V2? So, delta V2 divided by delta, so which is equal to 28 by 26, So, V2 will be equal to 1.076 volts roughly. So, this is V1 and V2. So, now what we have done, we have considered the node analysis to find the node voltages. Now, please remember, if you know the node voltages, you can find the response at any point of network, Say now we are interested in the current that flows in this direction, say I. Okay. Now, we have used the node analysis and have found the V1 and V2 to be 2.384 and 1.076. Now, I am interested in the current that flows through this conductance in this direction. So, can be easily found if you know the node voltages, like I is equal to this potential minus this potential into 4. So, V1 minus V2 into 4. So, V1 is 2.384 minus 1.076 into 4. Okay. So, this I will consider as 2.39 and this as 1.07 or rather 2.4 and 1 roughly. Okay. So, 2.4 and 1. So, it will be 1.4 into 4. So, 5.6 amperes, roughly it will be 5.6 amperes. So, now you can find what the response at any point of network if you know the node voltages. Okay. So, this is also one of the methods of analyzing a network. I hope this is now clear to you. Okay. So, today what we have done is we have started our discussion by considering the AC circuits, and AC circuits are nothing but the circuits which have what the resistance, inductance and capacitances, and those circuits which have resistances, capacitances and inductances along with the independent sources and linear dependent sources can be regarded as a linear circuit. And in those kind of circuits, if we consider the sources to be sinusoidal, even the responses will be sinusoidal of the same frequency as that of source. This we have to remember. Then what is the difference between the response and the source? Only the amplitude and the phase angle. So, what we discussed further was the representation of the source and responses in terms of phasors. Then we defined what is actually an impedance, which is actually voltage phasor to ratio of voltage phasor to current phasor. We also came across that the impedance is a complex quantity, but definitely not a phasor. Then we have represented the inductances and capacitances, which are actually expressed in Henry and farads into the in terms of what impedances, which take the units of ohms, so that we can apply what the KVL, KCL easily in the case of AC circuits. Okay, right. So, all those things we have discussed, and later on we took up a problem related to AC circuits, in which you have seen that the capacitances and inductances were represented equivalently in terms of their impedances, okay, in ohms. Farads and Henrys were represented in ohms, so that we could easily apply what the KVL and found the potential drops across those elements. Okay, so we came across a problem related to AC circuits under the mesh analysis. Then we found the capacitor current in that, okay, in that network using the mesh analysis. Then we started discussing about the node analysis. Let me tell you once again what is actually a node analysis, whatever that has been displayed here. So, here we identify nodes of the given network and consider one node as ground node, which is considered to be the zero potential point. We then identify the voltage at each of the remaining nodes, which is nothing but potential difference between a node of interest and the ground node, with ground node as reference. Node analysis involves the computation of node voltages, and when once these are found, we can find the response at any point of network, like what we did in this case. I was not known, but with the node voltages known could be easily found, right. So, the same problem whatever I have discussed has been displayed there. Okay. So, in the next class we will continue with the node analysis with some interesting problems. Okay. Then later on we will go to the concepts of super mesh and super node. Okay. Thank you.